welcome back to the data structure tutorial, and today we will be discussing about AVL tree, which is also called as height balanced binary search tree. Now what is the difference between normal binary search tree and height balanced binary search tree, and why we need this height balanced binary tree or the AVL tree? So let's take an example. Suppose we have the input symbols like 10, 11, or sorry, I'll take 10, 20, 30 and 40. So if you construct a normal binary search tree, how will you construct? You will be starting from 10. Now 20 is greater than 10. So you will be inserting to the right hand side because it is a greater than 10. Next input is 30. So which is greater than 10. So it will come to the right hand side. Again greater than 20. It will come to the right hand side 30. Now if we have an input 40, again it is greater than 10, greater than 20, greater than 30, so it will be inserted to the right hand side. So this is how we construct a normal binary search tree. But we are using binary search tree to search a particular element. So suppose now you want to search a element 40. So you need to compare with the 10, with the 20, with the 30 and with 40 as well. So you have a 4 comparisons. Even though it is a binary search tree, you need a 4 comparisons. So it has a high complexity to search that particular element because there is a fixed order for which you are searching for. Now if I draw a new binary tree with the same elements, let's say if I'm drawing like this, if it is 10 is the my root, if I sorry, if I make 20 as a my root node, then I can insert sorry, I'll take it here like this. Suppose 10 is my root node, then if I make 30 as my parent node, and I can insert 20 here and 40 here. The same elements I am using, but it has a different binary tree. So now if you want to search for the 40, you will have the comparison 1, 2 and 3. So automatically you reduced one comparison here, but it is also a binary search. You can see all the elements which are greater than 10 to the right hand side. 30 is greater than 20, so it is a parent. 40 is greater than 30, so it is a children to the right hand side. So it is satisfying the property of binary search tree. And this is also a balanced tree. Means you need to balance the height of your tree. Here you can see the height of tree is quite larger, and here the height of tree is only of 2 levels. So we'll discuss about how to calculate the height of tree and what is AVL tree now. So I hope that you understood that why we need to learn about the height balance tree, because if the height of tree is greater, then there will be a more comparison, so it means that more complexity of your program. So you can change the height of a tree with certain operations. And what are those operations? Let's discuss about that. So first of all, we need to understand what is meant by balance factor. So without balance factor, you will not able to perform the operations of AVL tree. So balance factor. So balance factor of any node of a node is equals to the height of left subtree minus the height of right subtree. So let us calculate a balance factor of any of the tree. So I will take some random example here. So C, I'll be writing D, E here, F, suppose G, and it has two children H and I. Now let us find out the balance factor of each node. So what is the height of left subtree means? You are considering one node at a time, and from that node to the longest leaf node, how many edges are there simply. So if you are considering A, and if you want to find out the balance factor, height of left subtree. So this is the left subtree and these are the two left children. So which is having the longest path. So D and E are at the same level. So you can consider any path. So how many edges you need? 2. So the height of left subtree is 2. So height of this left subtree is 2. So for this A, the balance factor is equals to 2 minus the height of right subtree. So what is the height of right subtree? It's 1 2, 3 and any of these 4 because both are at the same level. So it is 1, 2, 3, 4. So total length is 4. So the balance factor is 2 minus 4, that is minus 2. So the balance factor of A is minus 2. Now let us calculate the balance factor for B. So balance factor of for B is the length of the path to the child node is 1, left side 1, right side is also 1. So 1 minus 1, it is 0. So the balance factor is 0. For the C, let us calculate for the C that there is no left children. So the height of uh, left subtree is 0 minus the height of right subtree is 1, 2, 3. So it is 0 minus 3, it becomes minus 3. Let us calculate for the F. So balance factor is equals to left subtree's height 1, 2. So it is 2 minus there is no right subtree, so it is 0. So the balance factor is 2. For the G it is 1 minus 1. So it becomes 1 minus 1, that is 0. And for this also, for all the child node it is always remains 0. So we just calculated the balance factor. Now why we have calculated this balance factor? So if the property is if any node having balance factor other than 0, 1 and minus 1. If your balance factor is other than 0, 1, minus 1, then that node is unbalanced node. That node we can call it as a unbalanced node. And now in the given tree we have just calculated the balance factor. We'll mark the unbalanced node. So this is unbalanced node because the balance factor is minus 2. This is also a unbalanced node because we have a balance factor minus 3. We have this also unbalanced because the balance factor is 2 and rest of the nodes are balanced. So overall it means that your tree is not balanced tree, right? Because everywhere we need at least balance factor 0, 1 or minus 1. If other than this value we are getting the balance factor, means that nodes are not balanced, and then we need to perform operations of AVL tree, and those operations are called as rotations on AVL tree. So what are those rotations? So let us take one example for the rotation here. So there are different types of the rotations we have. So the first case we'll be taking, like for example we have the elements 10, then 20 and 30. We have a 3 elements. So if you calculate the balance factor for each node, the balance factor for this node will be 0 because there is no left right. For this 20 the balance factor is 0, left hand side 0 and right side 1. So 0 minus 1, it becomes minus 1. For the 10 it is 0 for the left hand side minus right hand side 1 and 2. So 0 minus 2, it becomes minus 2. So minus 2 is a balance factor for the root node 10. So it becomes unbalanced. Now we want to make this as a balance. So you need to rotate it. So how will you rotate? This type of rotation is called as right rotation. Right rotation means there are two right edges causing your node 10 to be unbalanced. So the rotation which you need to make is the left rotation of 10. Means you need to rotate this node 10 to the left hand side. So after rotation this tree will look like this. 20, 10 is rotating down towards the left, so it is rotated to the left children of 20, so it becomes 10, and 30 will remain at its own position. So you just rotated this 10 towards the left hand side of 20, means downward. Now if you calculate the balance factor, you will get a 0 minus 0. For 30 again it is 0, and for the 20 it is 1 minus 1 because left subtree having the height 1 and right subtree is also having the height 1. So the balance factor for this is 0. Now this is your balanced tree. Same way, we have another rotation. Suppose we have a tree. Suppose root node is 30. Root node is 30. Then we have a left subtree, suppose 20, and we have another left subtree as 10. So again, if you calculate for this example, the balance factor is for the 10 is 0, for the 20 it is 1 minus right side 0, so it becomes 1, and for the 30 it is for the left hand side it is 1 and 2 minus 0, so it becomes 2. So again this node is unbalanced. This is not a balanced node. So here again you need to make the rotation. The rotation is left left rotation. So this rotation is called as left left rotation. So how will you rotate this? So this 30 will be rotated towards the right hand side. So how will this tree will be constructed now? 10, 20 and 30 is rotated to the downward, means the right children of 20. Now again if you calculate the balance factor, it becomes 0, 0 and 1 minus this one, so it becomes also 0. So again it is a balanced tree. So you just rotated the tree which is causing the unbalancing of your node. Now the third case, let us take an example. Suppose you have the value 20 here, root node is a 20, then you have a greater value, suppose 30 here, okay, and now you have a value 25. So 25 is greater than 10, so it will be going to the right hand side, and smaller than 30, so it will be at the left hand side. So this is your binary search tree. Now again if you calculate the balance factor, for the 25 it is 0, for the 30 it is 1 minus 0, so balance factor is 1, and for the 20 the left side is 0 but right side is having the maximum height 1 and 2. So again the balance factor is minus 2, because 0 minus 2, that is minus 2. So this is an unbalanced node. Now this is the different case. Here you need two rotations. So this rotation is called as right left rotation. This rotation is called as right left rotation. So how to make this tree as a balanced tree? So what you can do, rotate this 25 towards the right hand side. So once you rotate this, it will look like this: 20, then 25. It will goes in between the 20 and 30, and 30 will remain there, right? So this is the rotation. You just rotating this 25 in between of 20 and 30. Now again if you calculate the balance factor, so it will be 0, it is 0, 1, so minus 1, it is 0, 1 and 2, so it is minus 2, and this is the case of right right rotation. So what you have done, now you just need to rotate this to the downward side. So what final balance tree you will get? It is 25, 20 and 30. So this is your final balance node. If you calculate the balance factor, it becomes 0, 0 and 0. So if this is the case, then you need to rotate it twice. One is right left rotation, and here you are rotating it as a right right rotation. Now let us discuss about the fourth case, and for that case we will take an example. Suppose we have a node 30 here at the root node, then we have a element suppose 20 here, and then we have a value 25 which is smaller than 30 but the greater than 20. Now again if you calculate the balance factor, it becomes 0 here. For the 20 it is 0 minus 1, so it is minus 1 here. For the 30 it is 1, 2, 2 minus right side is 0, so it is 2. So it is unbalanced here. Now again this rotation is called as left right rotation. So left right rotation. So what you need to do, you just need to rotate this 20 towards left hand side. So once you rotate it, your tree will look like this. It becomes 30. Now 25 will be the in between of 20 and 30. So this is the case. And then if you observe that again, if you calculate the balance factor, it becomes unbalanced, and this is the case of left left rotation. So you need to rotate this 30 towards the right hand side. So next, once you rotate the left left, then your final tree will be 25, 20 will be as it is, and 30 will be rotated to the right hand side, of your 25. So this will be your again a balanced tree. So whenever you will get a problem statement for balancing the height of any large tree, you will get all these four possibilities. So remember these rotations, every stage you need to calculate the balance factor. Whatever is unbalanced node, you need to consider three nodes from that node, and you have to apply the respective rotations. So in the next video, we will be discussing about a construction of a AVL tree with the sequence of elements.